I did it. But that feeling of victory often comes with a hidden cost for most engineers. You optimize your model to squeeze out every fraction of accuracy, celebrating the new soda number while ignoring the physical reality of running it at scale. The harsh truth is that 90% of AI projects fail not because the algorithm isn't smart enough, but because the hardware architecture cannot sustain the constraints required to keep it alive under load. We often treat chip selection as a simple shopping list problem, buying the device with the highest floating point operations per second and hoping for the best. This approach is fundamentally flawed. The reality is that raw compute power without architectural alignment leads to immediate deployment failure. Today, we're going to reframe how you think about GPUs and TPUs, not as purchasing decisions, but as the primary constraints on your entire system design. Most engineers fall into a trap where they trust the algorithm more than physics. A study of over 1,300 participants revealed a phenomenon called faith in AI, showing that even when predictions fail repeatedly, people treat the software as an authoritative predictor. In operational settings, this bias leads to losses up to 42% because teams prioritize prediction over guaranteed reliability. They assume that if they just throw more compute at the problem, it will eventually solve itself. But hardware has physical limits that no amount of code can override. When you ignore these constraints in favor of raw performance metrics, you build a system that looks impressive on paper, but collapses the moment you try to scale it beyond your local machine. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This disconnect becomes critical when we look at what actually happens inside massive data centers. Research analyzing 150 million hours of A100 GPU usage across two major clusters shows that hardware failures shift from rare anomalies to statistical inevitabilities as systems grow to tens of thousands of accelerators. While jobs using over 4,000 GPUs are the most vulnerable to crashing, they represent less than 1% of total workloads. This creates a dangerous blind spot where engineers focus on model accuracy for their specific tasks, while ignoring the reliability optimization needed for the majority of smaller jobs that make up the bulk of activity. The result is an ecosystem where large training runs are statistically fragile, and smaller inference services suffer from latency issues that raw flops metrics simply do not capture. A specific failure mode known as bursting illustrates this perfectly in adaptive controllers and real-time systems. When a system experiences stable periods lacking rich input data, model coefficients can drift into oscillation. This causes instability that is completely indistinguishable from standard software bugs, but originates entirely from the interaction between hardware dynamics and software logic. If your architecture does not account for these physical behaviors during design, you will spend months debugging code when the root cause is a mismatch in how the chip handles variable workloads over time. The industry sees this clearly in deployments like Meta's use of 16,000 A100s connected via high-speed InfiniBand networks. In that environment, network topology proves to be just as critical as the raw count of chips for preventing these inevitable crashes. Without a proper fabric connecting your accelerators, even the most powerful individual GPU becomes useless when it cannot communicate its state fast enough to prevent system-wide instability. The solution requires shifting your decision matrix entirely away from specifications and toward application constraints. You must stop asking which chip has the highest throughput and start asking what physical limits define your success criteria. Are you building for batch processing where latency matters less, or real-time inference where a millisecond delay breaks the user experience? Do you need reliability thresholds that account for statistical failure probabilities at scale? The data shows a distinct disconnect between workload types. Large training jobs consume massive resources, but are fragile without specific architectural support, while inference workloads suffer from cost and speed issues that no single benchmark can fully capture. Understanding this distinction is what separates junior engineers who just buy specs from senior practitioners who design systems for the real world. When you audit your projects with this lens, you begin to spot bursting risks and reliability blind spots before a line of code is written. You realize that hardware choice dictates architectural success in ways that no amount of hyperparameter tuning can fix. If you select an architecture optimized for high-throughput training but deploy it for low-latency inference, or vice versa, your project will hit a wall regardless of how accurate the model becomes. The goal is to align your physical infrastructure with your operational constraints from day one. This means evaluating network topology, memory bandwidth, and power delivery as strictly as you evaluate floating point performance. It requires accepting that some problems cannot be solved by simply buying more chips. They require rethinking the system design entirely. This shift in judgment is career-defining because it moves the conversation beyond model accuracy to deployment viability. You stop asking which model has higher numbers on a leaderboard and start asking if your infrastructure can actually sustain the deployment without crashing under load. It transforms hardware selection from a procurement task into a core engineering discipline that determines whether your project survives its first year in production. By designing for failure before you even begin, you ensure that your system is robust against the statistical realities of scaling to thousands of accelerators rather than relying on luck or better code alone. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.